Okay, so page 46. Now, I think number one, I think we got that all straightened out, didn't we? Am I right? Sort of, kind of. I got 2 seconds, the speed is 10 meters per second. We got 30 meters for the first one, right? It was the second one that was causing us the most grief. And the question is this displacement or is it distance? And if we add, the 40 is what's above, right? If we add the 22.5, then the 62.5 is in fact the distance traveled, but if we want to do displacement, then we would have to do what? Subtract, exactly. So that's how they get that answer. And it's odd that they sort of messed that up, but they not only messed that up, but they also messed up the actual numerical answer too in the book. So that allows you to work on their part. Okay, now did you guys understand kind of what they were talking about, number 2 and 3? You sort of know what you were supposed to do? Maybe? Okay, so 2A, uniform motion forward. Uniform motion means constant, right? So we are VT graph, so is that what you drew, Justin? That's what you drew? What about B? Uniform motion backwards? The thick line, of course, is the 0, right? And C, speeding up forward. Yeah? Everybody good there? Yeah. D is speeding up backward, right? Did they have these answers in the back? I don't think they did they? No. So that's probably why I went through these. Well, you got them out of there? Okay. That's a good idea. Okay. D is, oh, I've got 2 D's, don't I? This must be E, and this must be F, right? So E is slowing down forward. Now you'll notice, really, what's the difference between this D and that D? This is the actual E, right? What's the difference between those, really? The slope's exactly the same, right? One's positive, one's negative, exactly, right? Slowing down backward. Slowing down, the velocity has to approach what? 0. How'd you do on those? Pretty good? Yeah? Okay. Now, did you get what they meant in number 3? When they say produce simple scales ranging from 0 to 5, and then calculate the following. Well, in other words, put 5s everywhere. Okay? That's what they meant, right? So assume that that is 5. Assume that we're over 5 seconds. Did you understand that? That's what they wanted? Some of you? No? You just skipped 3?
Yeah.
Well, at least you're speaking up, right? Should I just leave that for a moment?
No.
This is really weird, you guys. It's like no one wants to say a word today. Oh yeah, well, calculate the acceleration. What would be the acceleration for this one? 0. This one? 0. How'd you get 1, Chris? Well, actually, I do know, but I want everyone to make sure everyone else knows. How did you get 1?
Acceleration is a slope.
Yeah, slope, right? Exactly. 5 over 5. 5 over 5. Oh, you said 5 and 5. You know. All right, down here, what would be the, this one here, we're looking for the acceleration, so we have -1? Yep, down 5 over 5. Very good, Darren. What about this one? Also -1. This one? That'd be +1, right? Slope is +1. All right. Now, we're also supposed to find the total displacement for each one here, too. Total displacement, we are looking at the what of the graph? Displacement. Area, right? So that first one would be 25. Second one would be -25. This one would be 12.5, half 25. This one would be the same thing, except it would be -12.5, 12.5, -12.5. Right? In fact, there's the answers for A, B, and C. I just realized I probably could go ahead of screen, right? And the average velocity, how do I find average velocity? Well, if it's constant, it's just 5. Right? Here it's going to be -5. Here it's going to be the, here you actually have to take the displacement and divide it by the time. Are we good to go on? Yeah? Okay, so here's probably D, E, and F. I'm thinking on the next slide. Okay? We've done the acceleration for all 3 of them. Here the displacement is a triangle, so it's going to be -12.5, The next one, triangle 12.5, but it's above, so it's positive. In fact, all the triangles are 12.5, aren't they? Okay. Average velocity here, you're going to have to take your displacement divided by 5. That's how you get minus 2.5. Same thing there, displacement over time. Same thing there, displacement over time. Nice, beautiful little multiple choice kind of questions for the test. Hint. Everybody good there? Okay, now number 4, from the DT graph in figure 1.18, generate a corresponding VT graph. You have to go all the way back to chapter 1 to find that. I had to help a few people find that there, but once you see it, I think they actually, don't they actually give you the slopes back there already? Right? This is the graph that they're talking about, and if you look to the side, they actually did the slopes for you. The slope of 0, slope of 12, slope of 31. So what do I have to do with this data right here? Just graph it, right? There's nothing to it. It's pretty simple. Right? It turns out it's not a straight line, is it? Anybody get a straight line out of it? That's what I got. Not really a straight line. It's kind of a stupid question. Yeah, it's kind of close, right? But with only 3 dots, I don't know. Not weird. All right, so I would like to move to 2.2 today. I'm going to give you guys time to work on those page 69 questions on tomorrow. I'll post those up online so those people that are awake can see them. But I would like to go to this one here, and I gave you this sheet. Some of you have found the stuff on page 47. You'll notice that I left off the velocity, acceleration, and the example there, okay? Because I would like you to jot it down, and that way sort of, get it in your brain, what's what kind of thing. So follow along with me. We're going to get to do some nice drawing here, too. It's going to be a lot of fun, Justin. All right. So this basically summarizes all the different kind of graphs that you have. So the first one here, let me just make this a bit bigger for us.
Are they using the bump?
Oh, they're right here. Did I get one? Oh, I'm sorry. I must have walked right past you. Yeah. Everybody else good? Riley, you got one? You were here when they were handed out? All right. So the first one here, we've got DT graph. We've got stopped, right? We've got stopped. So the DT graph, now here we're talking about the blue line, right? I'll just do this up here so you can see better. We're talking about that one there. So the corresponding velocity time graph would be flat, right? Because it's stopped. What does that mean for the velocity? Obviously, the velocity is 0. The acceleration is also 0. And an example, and they use the track participant there as an example. So I'm going to draw a nice little stick figure person waiting to start. It's a lot of fun because people can make fun of my drawing skills. I've been doing this for a while, Derek. Not bad, eh? I draw good stick figures. Now, see what you can do. The second one, they've got stopped as well, but it's a different version of stopped. How can there be a different version of stopped? I'm just going to highlight this for a second. You'll notice that the VT graphs are identical. What's different about the DT graph, or the second stop one there? What's different about it? It's below. So what does that mean in sort of in the track and field sense? Stop somewhere, just, pardon me? Well, you know what? I tend to hesitate to, or I tend to disagree with the book, okay? Let's just jot this down here first. Let's write velocity is 0 and acceleration is 0. They say that it means they're facing the other direction, but why do you think I would disagree with that? In fact, I'm not 100% sure that I agree with this one. If this is stopped and you're in a positive direction, then I'm going to put a line there. What do you think that line means or indicates? To start. Exactly. So for some odd reason, this person is maybe, got a head start kind of thing, Maybe it's like the little kids track and field meet kind of thing, and they've given the smaller kids a head start. Okay? So the second one, I think, is simply exactly the same. Why would this graph, why would that mean you're facing the other way? Because really it just means you're going to run that way, right? But you can't tell that from the graph. I'm going to say that it's exactly the same, except, no, I'll have to draw the rest, I guess, eh? Yeah, maybe I'll do this. Okay, maybe my drawing skills are good, but my computer skills are weak. I'm going to say it's exactly the same, just that what? You're behind the stop line. Does that make more sense to you, Darren? Yeah? If you want to do the other way, that's okay with that. I just think that that's a better representation of what's actually going on. Okay? Anyways. All right, so the next ones are constant velocity, right? Constant velocity running at a constant speed. So my dt graph here is increasing, but at a constant rate, which means my velocity time graph is above 0, right? So my velocity is, you'll notice they've got it, it's greater than 0, positive. The acceleration is what? Exactly equal to 0. How do I know the acceleration, Kelvin, is exactly equal to 0? Which is a flat line? Right. VT graph is flat, so it's 0. So what that means is the runner is actually running at a constant speed, right? Not accelerating, not slowing down. Let me see if I can do this one. Sometimes I put their arms coming out of their head. I have to watch that I don't do that. How's that? Did you know that I painted the stick figures on the wall in the gym 25 years ago? Did you? No, I made that up. Every time I say that, someone always says, "Did you?" Yeah. Thanks, man. I practiced last night just to be ready. Okay, so here we have the track and field guy, the bald-headed skinny guy, running at a constant speed. All right, now the next one, constant velocity. Now this one here, I will agree with. Constant velocity, back like this, right? Displacement time graph. How do I know it's constant speed?
No curve.
No curve, straight line, right? No curve, which means the velocity time graph is remaining the same. It's just below 0, it's negative. Here we know that the velocity is less than 0. What does it mean when the velocity is less than 0? Which means rounding backwards, right? Like backwards this way? Could be, I guess, right? It really doesn't matter what way they're facing, right? Really doesn't matter, although it would be kind of silly. They should have that race, the running backwards 100 meters. Okay? Did you know, here's my rant for the day, or my tangent for the day. Anyways, Mr. Vance. All right. So here we go. We got running backwards, right? Velocity is negative. Acceleration, once again, is equal to 0. And all this means is that the person is running at a constant speed, but backwards. Now, here's where I have a bit of an advantage. Because I'm going to do this.
Not going to work again.
No.
Told you.
Oh. Well, that's not too bad.
Still going the same way. Oh.
Think about crane. How's that? Okay, running at constant speed backwards. what you guys got out of it. Okay, so speeding up, the DT graph is curved, right? Speeding up, which makes the velocity time graph straight and increasing. Here, my velocity is greater than 0, and my acceleration is also greater than 0. And what happens when the velocity and the acceleration vectors are both in the same direction? Justin, what happens when the velocity and the acceleration vectors are both in the same direction? Say both positive.
I don't know.
Velocity and acceleration both to the right.
Both the same.
Yeah, I know, but what does it mean about the guy?
He's going positive.
That's just velocity positive. What if velocity
He's
and
speeding
acceleration? Speeding up. Good. I knew you'd get it eventually. Speeding up, right? Okay, so here we have somebody trying to catch Bolt, not being very successful at it, I'm sure. Right? Speeding up. Oh, I think I got the angle wrong there. And that's a very long lower leg. How's that? Speeding up to the right. So speeding up right, speeding up backwards is going to be like this. Okay? People sometimes get this one confused. How do I know that's speeding up? Because the slope here is getting steeper, right? It's becoming more and more negative. This is a graph of the slope, so it's getting bigger and bigger and bigger. So here my velocity is less than 0, and my acceleration is also less than 0. And as Justin pointed out, when the velocity and the acceleration are both in the same direction, then it is speeding up. So here's an example where the acceleration is negative, but the thing is speeding up. How can it be speeding up? Because it's pointed in the negative direction. If they're the same, it means acceleration. I'll do it the same as you guys. I'll try to draw this guy. All right, last couple here. Slowing down. How could I tell that the DT graph refers to a slowing down situation? Because the slope is doing what? Is it getting steeper or getting flatter? It's getting flatter. In both cases, it's getting flatter, right? Which means that the velocity is approaching 0. Here it's approaching 0 from positive because it has a positive slope. Here it's approaching 0 from negative because it has a negative slope at the start. Okay? So in this case here, velocity is positive, acceleration negative. Here we have the reverse. Velocity negative, acceleration positive. Right? So when they are opposite, then that means slowing down. Slowing down. Here the person is approaching the finish line. I'll have Ben Johnson putting his finger in the air, slowing down. I've actually gotten a lot better at drawing. Alrighty, so that's a pretty valuable sheet. There's lots of good information on there. You can certainly squeeze that down into a cheat sheet kind of thing for your for the test, but some pretty good information on there. Now, moving on in the textbook here, they talk about on page 48, and you guys don't have this on your sheet there, but it might be a good thing to have a look at anyways, okay? 48, they're into these flow charts. So if you need to construct a VT graph from a DT graph, okay? I think for the most part, what you've gone through in grade 11 should, be able to let you do this kind of thing. But there's the flow chart that sort of looks at that. Construct the VT graph under the DT graph, break the DT graph into distinct motion sections, extend the times down to the VT graph, calculate the slope at the start and the end of each DT graph section, mark the value or estimate on the slope of the VT graph. If the slopes are equal, then that means constant velocity, and it looks like that one or that one. If the slopes are not equal, then is the second slope greater than the first, and if that's true, then it's speeding up, and it looks like that or that. And if it's not true, then that means that they're slowing down, and the sections look like that or that. And I think for the most part, you may not understand that flow chart, but you probably can do those kind of questions. Okay, and I'm going to give you one right now, example number 5. I think you guys have that on your next page. Do you have this one right now? Page 219, or figure 219? Okay. So this one is relatively simple. Okay, but let's just sort of go through this one here. Okay, so we are going from DT graph. This is position time. DT. We're going to VT, and you did that already, right? But they made it a little bit easier for you. This one you're going to have to do a little bit of work. So what they're suggesting is that you should do it right below, right? Mark off sort of corresponding distinct sections, like that. Okay. Do you need to do this extended lines? Not necessarily. You should try to get them to match up. If they don't, they don't. Okay. I'm most interested in, I'm not really too interested in absolute values. I'm more interested in shape, although I should say from DT to VT, the exact values are a fair bit more important. Okay. All right. So now, do we have any numbers on the side here? Like, do we know what the scale is? No. So right away, what does that mean? Can we calculate the actual slope? No. So all I'm really interested in this one is the shape. Okay. So don't say, well, I don't know how to calculate the slope, right? So slope here is what? Positive, right? Positive slope. Here, slope is approaching 0, right? Although it does get flat awfully quick, doesn't it? Right? Here, the slope is 0 for the entire trip. Here, the slope is negative. And basically stays negative the whole way, right? Okay, so what does that mean to a corresponding VT graph? Positive slope, so start somewhere up here. I'm not really sure what that 5 is. Is it steps, you think? I don't know. There's 2 5s on there, though. I don't know. I'm not going to worry about it. Positive slope. This shows here, I'm going to show it in blue, this shows approaching 0, right? Slope approaching 0. The graph then has to approach 0, right? We're talking about the slope of this one giving us the value of this one, right? Slope is positive, approaching 0. Value is positive, approaching 0. Here the slope is a constant 0. So my value of my graph has to be constant 0. Right? Okay. Here the slope starts off 0 and then becomes negative, right? So it starts at 0, it becomes negative. Now it's curved, so that means that it's like close to 0 and then it becomes more and more negative. So it's actually increasing. But at some point, this line becomes straight, right? We don't know where that is. We're just going to say, well, they've got it lined up there, right? I wouldn't really care too much where it would be lined up. But at some point, that you should show a straight VT graph there, flat VT graph. Can you tell at all what's happening at that point right there? Troy, what's happening at that point right there in the displacement? Something special is happening. Yeah, it's going past the origin, right? Can you, should we mark that anyway on here? Is there any way to mark it? Not really, right? The only thing that might happen is because that's past 0, that means now the total displacement is 0, which would actually mean that the area here and the area there would have to be, yeah, opposite, right? One positive, one negative. But we're not going to actually show that on the graph, are we? So, in other words, don't worry about that. That's what I'm trying to say. Don't worry about that. Some people would try and they think that they'd have to go back to there, right? But that's not true because that's a velocity of 0. So don't do that. All right, so that's it. Basically, find the slope, find an estimate of the slope and then graph that estimate. That's all you really have to do. Okay? Any questions about that? Boring you to death. The next one is hard. Okay? If you need to stand up and, shake your arms, try to wake up, you might need to, because this one's hard. Okay? Going the other way is hard. How come? We're going the other way now. We're going to go from velocity time to displacement time. So this is the value, and this, again, is the slope. Let's break it into distinct sections. Okay? Let me just get this straight in my head here. All right, so you'll also remember that we're talking about displacement, right? So we've got here, as the velocity time graph, we've got a negative area there. I'm going to put negative in red, positive area in blue, positive, positive, 0, negative area. Okay? Here, what's happening to the velocity? The velocity is going from a negative value to 0. Right? The velocity is going from negative to 0. How do I know it's negative? Is it because of the slope? No. Remember, this is a graph of values, right? So here, my velocity is down below. It's a negative value, which means my slope here has to be also negative. And because this value approaches 0, this slope has to do what? The value approaches 0, so this slope also has to approach 0. So in other words, it's going to be negative, and then it's going to flatten off. Can you, if I had numbers on here, like say this was at -5 and that was say 2 seconds, the area of this, which would be -10, would be indicated where on the DT graph? Where would I put -10? It's a bit of a brain buster here. You can do it though. Natalia, do you know? No? Okay, remember the area of a DT graph is the displacement. How do I mark displacement on a DT graph? It would just be the value, right? So if those are my numbers, if I was -5 and 2, then that point there would be 10. That would line up with that one. Do I care about that in this situation? How come? How do you know I don't care about that? Because there's no values on the graph. I'm only concerned with the shape, so don't worry about that. All right. Justin, positive or negative velocity here?
Positive.
Positive velocity. What does that mean about the slope of this guy?
Positive.
Positive slope. What's the value at the start of this segment?
0.
And what's the value of it here? Some number, right? Some positive number, right? So in other words, we have to go from 0 slope to some positive slope, right? How do we know in this situation to stop before we get to that 0 mark? How do I know not to continue it to there? And this is probably the hardest question I've asked you today. How do I know not to go all the way to 0? Anybody know? Hunter? No? The only way to tell would be to actually calculate that displacement there, calculate that displacement there, find the difference, and then that would be where you would stop. Right? Yeah. That's okay if you didn't get that one. Hard question. Hard question. Okay, so I am at this point right here. Okay, what's happening, Chris? What's happening to the velocity during this segment right here? It does seem to be constant. How does that indicate it on a DT graph, constant velocity? Straight line going up? Well, it's right there. Why is it a straight line going up? Because it's constant velocity. How come it's going up? Because it's above its positive. That's good. Okay. So in other words, this is now a straight line. Now, I would say someone has screwed up here because the slope of this segment right here, should it not be exactly the same as the slope of this one right here? Right? Like this velocity is going up, say it's going like 0, 1, 2, 3, 4, 5, and then it stays at 5. Shouldn't the slope be the same? Shouldn't it be like that? It should be, right? So the art department screwed up there. Okay, but I do know these are hard to draw. In that situation, I would probably not deduct for that. That would be a bit of a meaty thing to do. But I would certainly want to see a straight line. Courtney, you're next. She takes a deep breath. What's happening to the velocity in this segment right there? What's it doing, the velocity? Decreasing to 0, right? So what does that mean about the slope on the DT graph then? Has to get steeper or flatter? Flatter, right? It's going to 0. So you'll notice, once again, right, we're going from here and then we're flattening off. Flattening off to 0. Okay? Riley, I'm going to give you an easy one. What's happening to the velocity right there, this segment?
It's 0
Is it staying at 0?
for that segment.
For that segment, yes. How is that indicated on a DT graph?
Same as indicated on the other one.
You mean, that's not good enough, I don't think. The velocity time graph is a constant 0, so what does that mean about the DT graph? It has to be? Has to be flat. That's the word I was looking for. Has to be flat. Has to be flat. Stopped. Okay, last one. Who should I pick on here? Adam? I don't think I've heard from you yet today. What's happening from the velocity for the velocity time graph from there to there? What's the velocity doing?
It's going negative.
So what does that mean on a DT graph?
You're gonna have a curve going.
It's gonna because it starts at 0, it's gonna start at flat
And then get bigger.
and then get, when you say bigger, what does that mean?
It's gonna,
Be more negative slope? Okay. Okay, so like that, right? Is that an easy question? No, it is not. Okay. I really have to put out all the distractions and I really have to think that through. Okay. There would probably be, if I did that kind of question, there would probably be 1, 2, 3, 4, 5, maybe 6 marks, 1 for each segment. Could you get part marks there? Absolutely, right? Would your graph look, could you get 5 out of 6 and almost have a completely different graph? I mean, if you had the first one wrong, right, and then after that you had everything right, you could still get 5 out of 6. They're hard to mark too. Okay? I probably wouldn't give you that many parts on test search. Okay, that takes quite a while to go through. Okay, done. I'm going to stop talking. You can work on for the rest of this period and likely most of tomorrow as well. The questions from page 69, I think they're 14, 18, 19, 18 to 21?
Yeah.
Okay. Page 69, 14, 18, and 18 to 21. On page 71 now you can also do 22 to 28, and I think what I did was I included those. Yes. Okay, so this black line master here, the second page of today, these are the graphs that they're showing you in the book. So all you do is you draw right below. Okay? This one on the back, this one is the final hand-in of all this stuff, okay? I will gladly help you with any of these. The hand-in, you're sort of kind of on your own a little bit. Okay, that's do you understand it? Okay, I will make that hand-in due Monday. How does that sound? Does that seem fair?
Nah, Tuesday.
Giving you a day and a half, Justin. Yeah?